When I first saw the early reports on 3I Atlas, I assumed it was just another interstellar visitor passing quietly through our system, but the deeper I went into the data, the more I felt that something about this object simply refused to fit the patterns we know. 3I Atlas was discovered on 1st July 2025 by the Atlas Telescope Network, making it only the third known interstellar object after Oumuamua and 2I Borisov. At first, everything about it looked routine. Its trajectory, its brightness curve, even its early coma formation matched what you might expect from an icy body crossing the inner solar system. But the more images appeared, the stranger the situation became. Multiple observatories, including amateurs, started reporting a diffuse green glow around its coma. One independent observer even captured a brief, isolated flash of green light detached from the nucleus, a reading that was quickly ruled out as a sensor malfunction. Yet the raw file showed no technical anomaly. Under normal circumstances, a green comet isn't unusual at all. For decades, we've understood the mechanism clearly. Ultraviolet sunlight excites diatomic carbon in a comet's coma, causing it to fluoresce an unmistakable green. The process is simple photochemistry. Whenever we see that color, we see C2. It's practically a rule of astrochemistry. So the expectation was obvious. Point a high-precision spectrograph at 3I Atlas, confirm the carbon signature, and move on. The Very Large Telescope in Chile carried out exactly that analysis. The spectrum should have shown the familiar C2 emission lines like a barcode across the green wavelengths. But the lines weren't there. The coma was almost entirely depleted of diatomic carbon. In other words, the very chemical needed to produce the observed green light simply didn't exist in any meaningful quantity. What we were seeing with our eyes contradicted what the spectrum insisted was true. And contradictions like this don't happen without a deeper cause. Either the visual observations were misleading, the spectroscopy was flawed, or our foundational understanding of cometary chemistry was incomplete. Given the quality of both datasets, the first two explanations seem unlikely. That leaves the possibility no one wants to state outright. The glow is being produced by a mechanism we do not yet understand. As I reviewed the data logs, I noticed something else. Around the same time that the green glow intensified, NASA's Swift Observatory detected unusually large quantities of water vapor venting from the object, nearly 80 pounds per second at a distance where typical comets remain frozen solid. A coma that dense, that cold, and that active raises difficult questions. Some researchers off record suggested the solar wind may be interacting with this water-rich plume in a way we've never modeled, creating a kind of plasma-driven emission. Others pointed out that an interstellar object could easily contain exotic compounds not found in our own system, any of which might fluoresce when struck by ultraviolet light. But then there is the detail that bothers me most. The green signature is stable. It doesn't vary with angle, rotation, or activity spikes the way a plasma interaction normally would. It behaves more like a chemical fingerprint, except the chemical responsible isn't there, at least not the one we expect. A few colleagues hinted privately that the missing lines in the spectrum might not mean absence, but simply unknown composition. Light emitted by a compound not in our catalogs would appear as noise rather than a neat barcode. And 3I Atlas does not come from our neighborhood. Its parent star could have produced materials that behave differently under solar radiation, leaving us with a glow we can observe but not decode. Still, that explanation feels too clean for the contradictions we're seeing. What unsettles me further is the silence surrounding the high-resolution data collected during the object's flyby of Mars. Instruments on Mars orbiters were perfectly positioned to record spectra at distances Earth-based telescopes couldn't match. That data certainly exists, but none of it has been released. Every inquiry I've sent has been met with the same vague reply: results pending internal review. When entire datasets disappear behind closed doors, I tend to wonder whether the problem is uncertainty or reluctance. For now, we know only this: 3I Atlas should not be glowing green, and yet it is. Whether the mechanism is plasma, chemistry, or something we haven't learned to name, the contradiction remains unresolved. What happens when an interstellar object defies the rules we trust the most? That question is going to matter even more soon, because in the next stage of its journey, 3I Atlas will face the sun directly, and that's when the real mystery begins. When the green paradox first emerged, I thought the next wave of observations would clear everything up. But instead of clarity, each new data set only widened the gap, and the more I looked at what wasn't being published, the more concerned I became. After weeks of preparation, 3I Atlas approached a critical phase in its orbit, the period just before superior conjunction, when the object would slip behind the sun and disappear from our view. This window was our last chance to gather clean data before months of silence. Dozens of instruments across Earth and Mars were positioned specifically to capture spectra before that blackout. Yet when I began assembling the comparative records, something strange happened. Several expected data sets simply weren't there. The missing pieces weren't random. They belonged to instruments that, in theory, should have produced the most revealing measurements. Mars orbiters, positioned far above the interference of Earth's atmosphere, had prime access as 3I Atlas crossed the inner part of its trajectory. Their spectrographs should have given us the first unambiguous confirmation of whether the green glow came from C2, exotic photochemistry, or something else entirely. Instead, the raw files vanished from public dashboards within hours of being logged. Technically, data can be flagged for review, but the timing felt too deliberate, and I am not the only one who noticed. A few colleagues contacted me privately, saying their requests for access were quietly redirected or left unanswered. One of them used a phrase I still find unsettling: "Someone doesn't want us looking too closely." Of course, there are reasonable explanations. High-value datasets often undergo internal verification to eliminate calibration errors. Agencies sometimes wait to avoid premature conclusions. But when the silence extends beyond the usual review cycle, I start questioning whether the issue is scientific uncertainty or institutional hesitation. While trying to piece together what remained, I focused on the confirmed anomaly, the object's massive release of water vapor. The amount, nearly 80 pounds per second at 3 astronomical units, contradicts everything we know about thermal activity at that distance. A natural comet should be dormant that far out. Yet 3I Atlas behaved as if it were already near perihelion. This unusual venting creates a unique environment around the nucleus, one potentially capable of interactions no current models can predict. Some atmospheric physicists told me, off record, that under the right conditions, a water-rich coma struck by high-energy solar wind could produce transient emissions unlike traditional auroral processes. That might explain the diffuse green glow, yet it still doesn't address why the spectrum lacks the corresponding emission lines. There is also a different possibility, far more difficult to quantify. If the object contains compounds formed in a chemically foreign star system, their spectral fingerprints would not match any molecule cataloged in our databases. The spectrograph would capture the light, but without a matching template, the instrument would effectively mark the result as noise. In that sense, the absence of C2 might not be a contradiction, but a sign of something entirely new. And that brings me back to the unpublished data. If any of the Martian instruments detected unusual spectral signatures, lines that did not correspond to known molecules, it would place large institutions in an uncomfortable position. Announcing unknown chemistry always carries a risk: misinterpretation, public speculation, or the possibility that the anomaly is a calibration artifact. Many agencies avoid that situation by waiting until they have overwhelming, reproducible evidence, but silence can be just as revealing as disclosure, especially when it concerns an object that has already defied several foundational principles of cometary physics. As 3I Atlas began disappearing behind the sun, the behavior of its coma changed again. Observers noted fluctuations in brightness that did not correlate with its distance or rotation. A few reported faint rhythmic variations, not strong enough to classify as pulses, but too regular to dismiss as noise. No one has offered a definitive explanation. Some suggested outgassing cycles. Others wondered if the dense coma was interacting with solar radiation in a periodic pattern. But the truth is simple: we don't know. And this uncertainty leads us to the next critical moment: perihelion. While hidden from view, 3I Atlas will encounter the most intense heat and radiation of its entire passage. Natural comets often fracture or disintegrate under such conditions. If this object survives largely unchanged, it would reinforce the idea that its structure, and possibly its composition, are far more robust than expected. In the coming weeks, every major observatory will be waiting for the moment the object reappears. Because when it emerges from behind the sun, the green glow may behave differently. It might brighten, fade, or shift to a wavelength we haven't seen before. Any of these outcomes would push the mystery further. For now, the unanswered questions remain. Why did the most valuable datasets disappear? What did the Mars orbiters see in those final hours? And what will 3I Atlas become after facing the sun's full intensity? We'll only know once it comes back into view. And that uncertainty, the silence between observations, is where the real tension lies. When 3I Atlas vanished behind the sun, I expected the days that followed to be uneventful. Superior conjunction usually forces a pause in observation, a simple waiting period before the object reemerges. But even without new images, the data coming from solar monitoring instruments offered an unexpected complication. Just days before disappearing, 3I Atlas had been struck by a coronal mass ejection, a powerful burst of solar plasma capable of tearing apart fragile cometary nuclei. Historically, CMEs have shattered comets far more stable than this one. If 3I Atlas were a typical icy body, the blast should have triggered a dramatic fragmentation event. But the CME hit, passed, and the comet continued almost unchanged. No outburst, no visible fragmentation, not even a significant distortion of its coma. It behaved less like an ice and dust aggregate and more like a cohesive, resilient structure. This anomaly forced me to revisit the mechanical assumptions we make about interstellar visitors. Oumuamua showed an unexplained acceleration. Borisov behaved more predictably, but its chemistry was unlike anything formed around our sun. Now, 3I Atlas adds a third category, physical integrity that defies expected tensile limits. Several colleagues quietly suggested the same idea. If the composition is exotic, the mechanical strength may also be unprecedented. A structure formed in a different star system, one with a distinct distribution of heavy elements, could naturally contain materials far stronger than those common in our region of the galaxy. The absence of C2 in the spectrum might indirectly support this. If the nucleus is dominated by complex carbon frameworks or unique refractory compounds, it would explain both the resilience and the spectral anomaly. But then there's the detail I keep returning to, the hollow density hypothesis. Before conjunction, several researchers ran revised mass estimates using reflected light curves and non-gravitational effects. Independently, their calculations pointed toward an unusually low density, so low that a standard cometary body should not remain intact. A porous structure could explain part of that, but not all. One astrophysicist reminded me of a point raised during the Oumuamua debates. A hollow shell can easily mimic an elongated low-mass object. Nature can generate porous aggregates, but a truly hollow body is far harder to justify. This is where the speculation becomes uncomfortable. A hollow configuration is useful for technology. It maximizes internal protected space while minimizing mass, a principle used in every engineered probe we've ever launched. To be clear, nothing in the current data proves such an interpretation. But the conditional logic is difficult to ignore. An object that is unusually strong, uncommonly light, and glowing through a mechanism we cannot identify invites questions that aren't easy to dismiss. While the object remained hidden, I focused on another clue, the unusual behavior of its coma. Swift's detection of persistent water release at 3 astronomical units still bothers me. Water ice doesn't sublimate at that distance under normal conditions. Some researchers propose trapped pockets of volatile material being exposed by rotational shedding, but the rate, nearly 80 pounds per second, is remarkably steady. That's not what sporadic fractures look like. It resembles controlled release or a sustained internal process. And that brings me to the small but significant green flash captured by Alexander Entropov, a flash spatially separated from the nucleus. One explanation is a brief burst of charged particles colliding with a detached fragment of vapor. Another theory, less commonly mentioned, is that the light originated from a mechanism within the coma itself, rather than from surface chemistry. If the object possesses layered materials or complex internal structures, deeper solar heating at perihelion could activate processes that our instruments would interpret as photochemical anomalies. As perihelion approached, solar observatories detected subtle fluctuations in the object's brightness, rhythmic, faint, almost like a slow pulse. These variations were too consistent to be dismissed as noise, but too weak to classify as signals. Some argued they were rotational modulation. Others wondered whether the dense, water-rich coma was interacting with the solar wind in periodic waves. What struck me was the timing. The fluctuations began shortly after the CME impact, as if the object absorbed the shock and responded through changes in its coma rather than structural damage. Then, during conjunction, an unexpected complication appeared in several datasets tracking the solar corona. A small region of enhanced green ward emission was briefly detected near the predicted trajectory of 3I Atlas. The readings were faint and lasted only minutes, easily overshadowed by solar activity. But the spectral pattern didn't match typical coronal emissions. A few analysts flagged the data, but the notes disappeared from internal dashboards within hours. Whether this was a coincidence or a glimpse of the object's behavior under maximum solar stress remains unknown. Soon, the object will re-emerge from behind the sun. When it does, we will be able to see whether it survived intact or suffered internal changes. Scientists are preparing to capture a new high-resolution spectrum immediately. If the green glow remains, the C2 paradox will deepen. If it vanishes, new explanations will emerge, possibly involving volatile loss or chemical transformation during perihelion. But the question that weighs on me most is the simplest. What kind of object endures a CME, vents water at impossible distances, glows in a color that contradicts its spectrum, and shows signs of a structure too strong for natural formation? Whatever comes next will either resolve the paradox or push it even further into unfamiliar territory. And when 3I Atlas steps back into view, we may not be ready for what we see. When 3I Atlas finally emerged from behind the sun, the first images were rushed, unprocessed, and full of noise. But even through the interference, one detail stood out immediately. The object had survived. Not fractured, not dimmed beyond recognition, not dispersed into a cloud of debris. It endured perihelion with a stability that feels increasingly difficult to reconcile with any natural model. The coma, however, was different. Its shape, once diffuse and symmetrical, now showed a subtle asymmetry, almost like a faint directional plume. Several observatories noted a narrow region where the brightness gradient steepened. At first glance, it looked like an outgassing jet, the kind that forms when subsurface volatiles are exposed. But the angle didn't match the expected rotational phase, and the plume's persistence suggested a sustained process rather than a momentary fracture. What surprised me most was the color. The green glow was still present, but its intensity had changed. Instead of the soft, diffuse halo we observed earlier, the emission now appeared more concentrated around the inner coma, almost as if the glow had retreated deeper toward the nucleus. Spectrographs recorded an enhancement in the green channel, but once again, without the expected C2 signature. The paradox not only remained, it had grown sharper. As I studied the early post-perihelion data, I noticed another pattern. The rhythmic fluctuations, which some had dismissed as noise before conjunction, returned, but stronger. They weren't obvious enough to call pulses, yet their regularity is unmistakable. Several teams tried to model the variations as rotational modulation, but the numbers refused to line up cleanly. The period was too stable to be driven purely by surface activity, and too slow to match typical cometary spin rates. The best description I can offer is that the brightness oscillates in shallow waves, rising and falling with an internal consistency that implies some organized process, or an interaction with a periodic external force we haven't yet defined. Meanwhile, the missing datasets continued to raise questions. When I contacted a colleague who had previously hinted at undisclosed spectra from Mars orbiters, he replied with a short, cautious message. We're being told to wait for the coordinated release. No timeline, no explanation, just a delay that grows more conspicuous as the anomaly deepens. Another colleague confided that preliminary spectra taken immediately after reappearance showed unexpected complexity. When I pressed for details, he stopped responding altogether. Then came something unexpected. Several radio telescopes scanning the region picked up brief broadband disturbances near the object's path. The signals were weak, irregular, and not modulated in any recognizable pattern. They could easily be artifacts. The sun's proximity complicates radio measurements dramatically. Yet the disturbances appeared in synchrony with the brightness oscillations. Not perfectly, but close enough to warrant attention. No one has claimed correlation publicly, but a few analysts noted the coincidence in private channels. Whether these disturbances originate from the object, the solar wind, or instrumental interference is still uncertain, but the most troubling development surfaced a few days later. A solar monitoring instrument recorded a fleeting, narrow spike of green ward emission at a wavelength not associated with known atomic or molecular lines. The detection lasted seconds, too brief for conclusive interpretation. Normally, such an anomaly would be discarded as noise, but the timestamp placed the spike directly along the predicted trajectory of 3I Atlas as it passed through a region of enhanced solar wind. When I tried to access the raw file again later, the entry had been flagged and temporarily restricted. The timing of that restriction, combined with the growing list of unpublished data, is becoming difficult to attribute solely to routine review. All these observations, the concentrated green glow, the consistent oscillations, the asymmetric coma, the unexplained radio disturbances, might ultimately have straightforward explanations. Exotic chemistry, unusual plasma interactions, or rotational effects amplified by perihelion heating are all possibilities, but none of them comfortably account for how intact the object remains, or why its spectral imprint still contradicts the color we see. Some researchers, speaking cautiously and always off record, suggested that 3I Atlas may be composed of layered materials with varying responses to heat. If perihelion stripped away outer inert layers, the exposed interior could fluoresce differently. Others propose that the object's low density is the key. A hollow or semi-hollow structure could insulate internal regions, releasing energy in periodic cycles as it passes through uneven solar wind streams. But one interpretation continues to hover in the background, the one almost no one wants to voice. If an interstellar object were constructed rather than formed, perihelion would not necessarily destroy it. It might activate it. A temperature-induced change in emitted light, localized plumes, and rhythmic variations could all fit within the broader category of engineered responses, even if no one is prepared to make that claim officially. For now, the situation remains unresolved. The object's behavior is becoming more unusual, not less, and the data that could resolve the contradictions continues to trickle out slowly, filtered through layers of institutional caution. As new spectra are being processed, one question is becoming increasingly urgent. What will the next high-resolution analysis reveal? A familiar pattern we failed to recognize, or a signal that forces us to redraw the boundaries of what we consider natural? Whatever the answer is, Part 5 will bring us to the edge of the mystery. When the new high-resolution spectra finally arrived, I expected clarity. Instead, what I saw felt like stepping into a deeper layer of the same puzzle. The data didn't resolve the contradictions around 3i Atlas. It sharpened them. And for the first time in this investigation, I understood why some institutions seemed hesitant to publish their results. The green glow persisted, but its spectral structure changed in a way I wasn't prepared for. Instead of the chaotic noise we observed earlier, the post-perihelion spectrum showed several faint, narrow emission features that do not correspond to any known molecular lines. They weren't strong enough to identify, nor random enough to dismiss. They sat at irregular intervals as if belonging to a compound with a complex, unfamiliar structure. The C2 signature remained absent. The paradox, a green comet without diatomic carbon, now had an additional layer, a glow accompanied by spectral features that resist classification altogether. As I compared the results with preconjunction measurements, something else stood out. The brightness oscillations, once shallow and barely detectable, now formed a clean, repeating pattern. It wasn't perfectly regular, but close enough to suggest a stable internal mechanism, or a persistent interaction with the solar wind. Several researchers proposed plasma wave resonance within the unusually dense water-rich coma, but their simulations couldn't reproduce the observed periodicity. One analyst pointed out quietly that the oscillations resembled thermal cycling in layered materials subjected to uneven heating. That comment, though entirely physical and grounded in known processes, lingered with me longer than it should have. At the same time, radio observatories monitoring the object's path recorded intermittent broadband fluctuations that aligned, approximately, with the peaks of the brightness cycle. The signals were too faint to be called emissions and too inconsistent to suggest communication, yet they also failed to match common sources of solar interference. When I asked a colleague for the raw files, he told me the data was being reprocessed, though he didn't clarify what that meant. Meanwhile, several teams reported structural coherence in the inner coma that should not exist. Natural comets, especially those battered by perihelion, often develop chaotic jets and asymmetric release patterns, but 3i Atlas maintained a smooth, stable inner region as if shaped by an underlying geometry rather than random outgassing. Instruments tracking motion within the coma noticed that particles moved in well-defined arcs, not turbulent spirals. One physicist suggested that the object may possess a rigid inner shell providing an anchor for gas flow, a hypothesis consistent with the low-density estimates reported before conjunction. But the detail that stayed with me most came from a short, ambiguous note attached to a restricted data set. It mentioned a localized enhancement of green ward emission near the subsolar point, lasting less than a minute, recorded as the object exited perihelion. The brief note speculated that the enhancement might indicate the exposure of deeper material or an internal thermal event. The file was pulled from public access shortly after being posted. When I tried to inquire about it through official channels, I received no response. Even so, the overall pattern is difficult to ignore. A resilient structure, a glow that defies spectral expectations, unknown emission features, rhythmic brightness cycles, radio fluctuations, and an unusually ordered coma. Each anomaly can be explained individually, with effort, but taken together, they form a pattern that resists simple categorization. Naturally, some theories emerged, quiet, cautious, and always framed as speculation. One interpretation suggests that 3i Atlas may consist of layered exotic materials that release energy differently depending on temperature, solar pressure, or plasma flow. Another points to the possibility of photochemical processes involving compounds formed in environments unlike those in our own star system. A third proposes that the hollow density signature could indicate a structure shaped by processes unfamiliar to planetary formation models. All of these explanations remain hypothetical. None are confirmed, but they reflect the same underlying truth. The object behaves unlike anything we have studied before. And then there is the silence. Several datasets expected to be released after re-emergence remain withheld. Internal reports circulate quietly, but nothing official is published. The laboratories I contacted either responded cautiously or not at all. Some of the individuals who initially shared insights with me have since stopped answering messages. Perhaps they are simply busy, or perhaps the extraordinary nature of the data has forced institutions to adopt a more conservative posture. For now, 3i Atlas continues its outbound trajectory, gradually fading as it moves away from the sun. It will remain observable for several more months before disappearing into the darkness from which it came. And unless something changes, unless the missing data is released, we may be left with questions that will outlive the object's brief passage through our system. What we witnessed may be only a fragment of a much larger story, a reminder that interstellar space can deliver surprises that challenge not only our models, but our assumptions. Whether 3i Atlas is simply an unusually complex natural visitor or a sign of something we have not yet learned to recognize is not for me to decide. All I can say is this: the mystery remains unresolved, and somewhere beyond the edge of our instruments, the object is already carrying its unanswered questions back into the dark. Whether its silence is natural or deliberate is something each of us must decide for ourselves.